Okay, couple quick reminders before we go on. One is it's important to remember that probability distributions are based on theory. They're based on what we might observe if we had the time and the resources to conduct an infinite number of experiments, an infinite number of research. And when you think about an infinite amount of research, and when you think about that infinity, what is infinity? Well, infinity is everything. Infinity goes on forever and ever. It can be a little bit difficult to wrap our heads around what we mean by an infinite number of trials, but suffice it to say, the next probability distribution we're going to examine is based on theoretical explanations of phenomenon, the reason things happen. It's known as the normal probability distribution, also known as the bell curve in some circles. And the bell curve, if you'll just pay attention to the shape first and foremost, it's called a bell curve because it's kind of shaped like a bell. Now, there's a couple of documents that you might want to access, so if you want to get those, if you don't have them already, you can pause this video and obtain those. The two documents I'm going to reference here is one is called orientation to the normal probability distribution, and the other one is called, it looks like this, although I know that's kind of nondescript, it's just like typing. This one is called Intro to the Normal Probability Distribution, and these two documents kind of go hand in hand. Orientation to the probability distribution and introduction. So you might want to have the two of those with you, while you watch this video, or have them both together when you review and study these materials. Basically, a couple things I want to orient you to this particular drawing, this normal probability distribution. First, although this particular version is hand drawn, assume that it is not hand drawn. Assume that it is absolutely perfect. So, if you will buy for a moment the assumption that it is perfect, I want to point out a couple of things about it. One is that this drawing is symmetrical. And when we say that something is symmetrical, that means that we could cut it in half and have two exact mirror images of each other. Feel free to ignore for a minute the fact that I've divided this into pieces. If we just cut it in half, we would have two exact mirror images of one another. Now, because it's symmetrical, that also means that if we divide each half equally into pieces, that certain pieces have to be equal to each other in size. So, for example, piece A is equal in size to piece F. Piece B is equal in size to piece E. Piece C is equal in size to piece D. All right. So also another vocabulary word that I want you to be aware of is the word abscissa. A-B-S-C-I-S-S-A. Abscissa. Abscissa. It's not the kind of word we say every day, but we say it in stats because it has a very special meaning. The abscissa is this horizontal line below the probability distribution. That's the abscissa. So when I refer to the abscissa, that's what I'm talking about. Now, you may have already seen, if you have keen eyes on this YouTube video, or if you've already obtained the drawing and examined it yourself, you have seen along the bottom, along the abscissa, there are Z. The letter Z is written several times. Well, guess what? Those are Z-scores, because here's the deal. We can navigate the normal probability distribution, the normal curve. We can navigate the normal probability distribution using Z-scores. And in fact, I would go so far as to say that Z-scores are the language of the normal probability distribution. In other words, we're going to use Z-scores and the Z formula to solve a lot of different types of problems about the normal probability distribution. So keep that in mind. What I want to, I also want you to be aware of this line right here You know what that's called? That line that goes across the top of the probability distribution? It's named the same thing as any other line that goes across the top of a probability distribution, and that is the curve. That is the curve. And so everything that falls under the curve is referred to as area under the curve. Area under the curve. This whole area here is the area under the curve. And guess what? That area, if we added it all together, would equal 1. Or, expressed as a percentage, it would equal 100%. Now, if you have a very keen eye, you may have already noticed that the curve and the abscissa do not touch. They never touch. They go on and on and on forever, getting closer and closer and closer together, but they never actually meet. That means that probability goes on forever. That means the probability gets infinitesimally smaller and smaller and smaller. Let me draw a picture, let me draw a little extension of what I mean by this, although as many of you already are highly aware, I'm really not that good of an artist. But we could extend that probability distribution out forever, and those two lines would keep getting closer and closer together, but they would never meet. Also, although hopefully this is self-evident at this point, the area under the curve is associated with specific amounts of probability. So in other words, the size of the piece is associated with probability. So hang with me here, because I know this segment's going a little bit long, but look at this drawing and imagine it not as a drawing, but imagine it as a dartboard. Okay, so imagine I set this up as a dartboard. I think the glare might be getting the best of this. It's probably going to scuff my paint. But if I put that drawing on the wall and it was a dartboard, and I asked you to throw a dart at that dartboard, which pieces do you think are most likely going to be hit, right? Just by chance alone. Piece A, B, C, D, E, or F. Which two pieces, you just have one dart only, which two pieces do you think are most likely to be hit? I hope that you said pieces C and D. And why did you say that? Well, because C and D are the biggest, right? They're the biggest pieces, and together they form the biggest pieces, or the biggest piece together of the probability distribution. What's the next most likely? What are the next, if you exclude C and D, what are the next most likely pieces to be hit? A, B, E, or F. I hope you would say piece B and E, or pieces B and E, because they're the next largest. After that, piece A and F are the next largest. So the only point that I want to make by going through that little exercise is to demonstrate that the area under the curve is associated with specific amounts of probability. And that, again, getting back to something we mentioned in an earlier segment, that is really what inferential statistical testing is all about, determining what is the likelihood that we would observe what we did. Now, in this case, I'm asking you to speculate about the likelihood of hitting a certain portion with a dart, right? But it still demonstrates the same point. What's the most likely outcome? If I gave you one dart and said you can name two pieces on where that dart is going to land on that drawing, you would probably be best served by saying, well, if Dr. Holsinger is going to let me pick two pieces, I'm going to pick C and D, because those are the largest pieces, and that means that this dart, if this were a dart, is most likely to land there.